The science of anthropogenic global warming is well over 150 years old. In fact, by the end of the 19th century, the primary mechanisms of how global warming could occur, and specifically how humans would contribute to it, were already understood and had been verified both experimentally and through scientific observation. In 1824, French physicist Joseph Fourier proposed that the Earth's atmosphere could act as an insulator, increasing global temperature. The most important observation made by Fourier was that human activity, combined with natural processes, would accelerate global warming. It's worth reading his entire statement. Quote, "The establishment and progress of human society and the action of natural powers may, in extensive regions, produce remarkable changes in the state of the surface, the distribution of waters, and the great movements of the air. Such effects, in the course of some centuries, must produce variations in the mean temperature for such places." End quote. This was a groundbreaking conclusion, firstly because it identified an atmospheric feedback mechanism by which global temperature could increase over time, and secondly because it stated explicitly that human activity could contribute significantly to this mechanism, and therefore increase the speed and extent of global warming. These two premises laid the foundation of anthropogenic climate change science, and over the next 130 years they would be proved true repeatedly by an overwhelming accumulation of scientific experimentation and observation. From 1827 to 1838, Claude Pouillet built on Fourier's work and was the first to propose that both carbon dioxide and water vapor were greenhouse gases which could trap infrared radiation within the atmosphere, causing global warming. Although Pouillet demonstrated this mathematically, he did not validate his model experimentally. In 1856, American women's rights activist and scientist Eunice Newton Foote concluded from her own experiments that carbon dioxide has an insulating property which can increase the Earth's atmospheric temperature. Although her conclusion was correct, her actual results did not support her conclusion. However, that's a subject for another video. Check the links in the description. Several years later, in 1859, English physicist John Tyndall's experiments finally proved that both water vapor, H2O, and carbon dioxide, CO2, are greenhouse gases capable of raising global temperature. In an extensive 40-page paper published in 1861, Tyndall acknowledged the work of earlier scientists, cited previous relevant experiments, formed a specific hypothesis, and described in detail his own experiments, which he carried out with new instruments made specifically for the purpose. This was the first definitive experimental evidence for the greenhouse gas theories of Fourier, Pouillet, and Foote. In 1886, Samuel Pierpont Langley's experiments decisively proved Fourier's greenhouse effect theory was correct. 10 years later, in 1896, Swedish physicist and chemist Svante Arrhenius used Langley's data to estimate the extent to which increased carbon dioxide levels would raise the global surface temperature through the greenhouse effect. This work by Arrhenius was the next major breakthrough in climate change science, providing a mathematical formula for predicting the relationship between atmospheric carbon dioxide levels and global temperature increase. His formula is still used today. In 1896, Swedish physicist Arvid Högbohm, who worked with Arrhenius, was the first to provide calculations demonstrating that human activities were increasing atmospheric carbon dioxide. Using these calculations, Arrhenius predicted that doubling atmospheric carbon dioxide would raise global temperature by 5 to 6 degrees, but also calculated that at current industry levels it would take several thousand years, and that the ocean would act as a carbon sink to offset the effect. So by the end of the 19th century, it was understood that human activities could increase atmospheric carbon dioxide levels to the point that global warming could occur. However, there was no concern since it was assumed that this would not take place for thousands of years. Part 2 of this series will demonstrate that this conclusion turned out to be dangerously wrong. The opening of the 20th century saw a significant change in scientific commentary on anthropogenic global warming. In 1908, Arrhenius noted a large increase in coal burning and calculated that this could increase atmospheric carbon dioxide significantly in mere centuries rather than thousands of years. However, he believed this would be an advantage, resulting in a climate more suitable for human habitation and crop cultivation, writing, quote, "We may hope to enjoy ages with more equable and better climates, especially as regards the colder regions of the earth, ages when the earth will bring forth much more abundant crops than at present, for the benefit of rapidly propagating mankind." End quote. The issue of anthropogenic global warming also started being mentioned repeatedly in the press. In 1912, the Braidwood Dispatch and Mining Journal noted that CO2 produced by coal consumption could increase the Earth's temperature in a matter of centuries. In 1922, the Monthly Weather Review observed warming of the Arctic and loss of ice coverage. In 1932, a newspaper article described, quote, "conclusive mathematical evidence that the Earth's temperature is being warmed by the increased amount of carbon dioxide present in the atmosphere," end quote, and attributed this to both human industrial activity and animals. In 1934, the Cairns Post cited the British Meteorological Office saying, quote, "The world is gradually becoming warmer and drier," end quote, and warning of the melting of the polar ice caps and a rise in sea levels. Several of these articles carried alarming headlines and startling predictions, such as warning of disappearance of the Arctic within a few decades. It must be understood that these claims were the product of journalism rather than science. There was no scientific consensus that such large-scale events would happen in such a short time. In fact, most scientists believed the effects of climate change would not be felt for many centuries. Even at this point, there were still scientists who did not believe carbon dioxide levels would ever have a significant effect on global warming. George Simpson of the British Meteorological Office stated with confidence that it was, quote, "now generally accepted that variations in carbon dioxide in the atmosphere, even if they do occur, can have no appreciable effect on the climate," end quote. Additionally, most climate scientists who accepted that anthropogenic global warming was possible were still convinced that it would take a very long time and would have a net benefit on the Earth's climate. In the 1930s, US engineer Guy Callender observed that US and North Atlantic temperatures had risen, writing, quote, "Man is now changing the composition of the atmosphere at a rate which must be very exceptional on the geological timescale," end quote. Nevertheless, despite identifying this as the start of definitive anthropogenic global warming, Callender was unconcerned, concluding the effect would ultimately be positive. Up to about 1950, although carbon dioxide was accepted as a greenhouse gas, and it was recognized human activity could lead to global warming, it was still doubted that human industry could produce climate-changing levels of carbon dioxide, or that anthropogenic global warming could be modeled successfully due to the huge number of variables involved. During the 1950s, massive advances in science and computing provided more accurate modeling, and it was realized that the ocean would be unable to absorb sufficient carbon dioxide to prevent global warming. Scientists such as Gilbert Plass, Roger Revelle, and Bert Bolin started sounding the warning that anthropogenic global warming was now a genuine scientific concern. In 1956, Plass predicted that doubling atmospheric carbon dioxide would increase global warming by 3.6 degrees, that CO2 levels would increase by 30% over the next 40 years, and that the global surface temperature would increase by 1 degree by the end of the century. These predictions proved remarkably accurate. 50 years later, the International Panel for Climate Change's fourth assessment report recorded a climate sensitivity of 2 to 4.5 degrees, compared with Plass' estimate of 3.6, a 37% increase in CO2 levels, compared with Plass' estimate of 30%, and a global surface temperature trend of 0.7 degrees, compared with Plass' estimate of 1 degree. So by the 1950s, accurate long-term climate change predictions were starting to become possible.
I can show you how carbon dioxide affects Earth's climate using this heat-sensitive or infrared camera which is purring away here, and a candle, this glass tube which is hooked up to this rather large canister of carbon dioxide gas. Now if I light the candle, you'll see that on the monitor the camera picks up the flame perfectly. Look at that, the hottest parts are glowing white. Now watch what happens when I turn on the carbon dioxide. Just keep your eye on the flame. The gas is invisible, so you don't see it fill in the tube, but as it comes in, you should see the candle start to disappear. There it goes. Look at that. What's happening is that the carbon dioxide in the tube is effectively trapping the heat. The candle's warmth no longer reaches the camera. Instead, it's absorbed by the carbon dioxide inside the tube.
Part of me wished I spent 10,000 hours learning to play the guitar instead of learning computer animation. But anyway, here we go. Carbon dioxide, infrared or IR activity. You need to learn these 3 stretching and bending motions that the carbon dioxide molecule can do. If the molecule just happens to be making one of these motions as it's hit by an infrared photon, then one of 2 things can happen. If it's infrared inactive, like the one on the left, then the photon will just pass straight through. But if it is infrared active, the motion, then the infrared photon will be absorbed and then re-radiated by the carbon dioxide molecule. It is of course re-radiated in a random direction, but I've shown them being re-radiated back down. So you can see the carbon dioxide is acting like some kind of mirror. It's reflecting back the infrared or the heat, electromagnetic radiation from the Earth, which would be at the bottom in this diagram. So how can you tell if a motion is infrared active or infrared inactive? Well, the long and short of it is, if the motion causes the dipole to change, then it is infrared active. So for carbon dioxide, they're going to want to know which of these is infrared inactive, I'd imagine, and that's the symmetrical stretching. The dipole of the carbon dioxide doesn't change when it undergoes symmetrical stretching. All of the main 3 water motions for the molecule, asymmetrical stretching, symmetrical stretching and symmetrical bending, all of these involve a change in dipole for the molecule. And so that means all of these motions are infrared active, and so infrared light from the Earth will be absorbed and then re-radiated, potentially back down again, to the planet, thus keeping us warm. And so this is how the 2 molecules behave as greenhouse gases. You don't need to know how methane, the other molecule mentioned in the syllabus, actually behaves like a greenhouse gas in this detail.
Our planet's atmosphere has been warming recently, and the cause is something called greenhouse gases. But what exactly are greenhouse gases, and how do we know they cause our planet to warm up? The objects on this table are at room temperature, each more or less as warm as the objects next to it. But some things are warmer than others, like this cup of tea. Because the cup of tea is warmer, energy is flowing from the tea to the room around it, in the form of infrared radiation. By using an infrared camera, we can watch the cup of tea cool as it transfers energy to the room. Over time, it will reach the same temperature as the other objects around it. In science, this transfer of energy is what we call heat. Now, let's step back and imagine our planet. Our sun is continually transferring some of its energy to our planet. Much of that energy travels right through Earth's atmosphere and reaches the surface, where it is absorbed and re-emitted into the atmosphere in longer infrared wavelengths. If all of that energy passed through the atmosphere directly into space, our planet would be quite cold, on average around -18 degrees Celsius. But infrared energy can interact with certain gases in the atmosphere, which are known as greenhouse gases. These gases interrupt the flow of energy escaping from Earth, holding some of that energy in the atmosphere. It is a little like throwing this towel over this heating pad. The towel interrupts the flow of heat, trapping the energy near the surface of the pad. A simple experiment will demonstrate which atmospheric gases behave in this way. Here are 4 cylinders filled with 4 atmospheric gases: nitrogen, oxygen, carbon dioxide, and methane. Notice the gases are transparent to visible light, just like the atmosphere. But in this experiment, we'll test which ones are transparent to infrared light. This heating pad emits infrared wavelengths and will simulate our planet's surface. We've sealed the ends of each cylinder with thin plastic wrap, because glass itself blocks infrared radiation, but the thin plastic doesn't. We'll start with a cylinder filled with nitrogen gas and place it between the infrared camera and the heating pad. Looking down through the cylinder, we notice that the infrared energy passes right through nitrogen without being absorbed. If we try the cylinder filled with oxygen gas, we get a similar result. But carbon dioxide is a different story. Notice how the image in the infrared camera becomes much cooler. This reveals that the carbon dioxide is absorbing some of the infrared energy given off by the heating pad before it can reach the camera. And here's methane. Methane also absorbs the infrared radiation. So, greenhouse gases, like carbon dioxide and methane, are gases that absorb energy, trapping more energy in the atmosphere. But to see if greenhouse gases actually behave this way in the atmosphere, we have to move from our tabletop experiment to the real world. The first piece of evidence comes from a satellite measuring the wavelengths of infrared energy escaping from Earth's atmosphere. Since the precise wavelengths absorbed by each greenhouse gas are known, the satellite should detect gaps at those precise wavelengths. This curved line shows what would be detected if no gases were absorbing energy. And this squiggly line shows the real measurements from the satellite. The difference between the curved line and the squiggly line reveals the energy being absorbed by greenhouse gases. These wavelengths here are missing because of carbon dioxide, and this dip is caused by methane. And these gaps show wavelengths absorbed by water vapor and ozone, 2 other important greenhouse gases. This is the energy that doesn't escape through the atmosphere and remains behind to warm the planet. Next, we have to see if a change in the amount of greenhouse gas in the atmosphere causes a rise in global temperature by looking at things over time. Here is a chart that shows a 40% rise of atmospheric carbon dioxide over the last 60 years. And here is a chart that shows global temperature over the same period. The average surface temperature of our planet has been rising at the same time as we've been putting more and more greenhouse gases, like carbon dioxide, into the atmosphere. So, given our little experiment and the evidence from real-world measurements, it is very difficult to ignore the fact that greenhouse gases are causing our planet's climates to change. And once we realize this, we have to ask ourselves, what are we doing about it?
Svante Arrhenius was a highly celebrated Swedish physicist and chemist who was instrumental in the early discoveries of greenhouse gases and their effect on the global climate. His work in the late 19th century focused on the cause of the great ice ages of centuries past. He concluded that greenhouse gases, such as carbon dioxide, could cause a rise in world temperatures and therefore prevent another ice age. His findings formed the basis for further research into the existence and causes of global climate change.
The greenhouse effect, as we now call it, was well known by the middle of the 19th century, that the Earth would be very, very cold if it didn't have an atmosphere. So the question is, what's the effect of the atmosphere and what's the effects of the constituents of the atmosphere? Well, so Arrhenius was making calculations of this, and did you know that the amount of carbon dioxide that humanity puts into the air through its industry is comparable to the amount that comes from volcanoes? So we're actually, we're adding 1,000th part to the atmosphere every year. So if that's so, then in 1,000 years it'll double. You see, notice that at that time they didn't realize that the population was doubling every generation, and they didn't realize that the amount of industry per person was doubling every generation. So the amount of carbon dioxide emitted quadrupled in every generation. You just said, if every year we emit 1,000th part to the atmosphere, then in 1,000 years maybe it'll double, and what'll that do? And he did some back of the envelope calculations. It might warm with the Earth a few degrees in 1,000 years. Well, that'll be nice if it ever happens. I mean, this is Sweden.
And the other fellow that I think inspired Arrhenius, in fact, he did his work the year Arrhenius was born, was John Tyndall at the Royal Institution, and he was basically an infrared sort of jockey. He put up an experiment that he could put any gas in a tube, and he could run an infrared signal through it and watch its attenuation. So he discovered that water vapor really controls the heat budget of the Earth, and that CO2 is an equal in absorptive capacity. But he observed that these trace elements have a greater effect on the Earth's atmosphere than the sunlight, because they're forming a barrier, they're forming a one-way filter.
Well, of course, the theory was first established in 1896 by Arrhenius, but then there was a long period when, with some notable exceptions, not much was going on, and it was kind of an arcane question that was a minor sidelight in the larger scientific endeavor.
And the individual that I studied in that middle of the 20th century, early 20th century, was Guy Stewart Callendar, who was extremely well educated. His dad was the most famous physicist in Britain at the time, and he was able to put together infrared band observations that the astronomers and the physicists were doing. And he was able to put together the early uptick in 20th century temperatures.
And he had the gall to go and tell the Royal Meteorological Society that he knew why that was so. It was because the carbon dioxide had been going up. And as we now know, he was right. He was able to pick the right measurements, but people at the time weren't at all sure they had picked the right measurements, and they certainly weren't convinced that the temperature rise was due to carbon dioxide. It was just some large natural cycle going up and down. Callendar persevered, though, and just kept after him year after year.
When Callendar began his meteorological work in 1938, he did so as a hobby to take up his spare time. His insight into how CO2 could affect the warming of the planet was met with criticism, but ultimately his work and theories made him one of the great pioneers in the study of climate change.